In this lecture, we study recursive data types, types that are defined in terms of themselves. We will implement immutable lists using the empty and cons variant pattern and explore how the interpreter pattern distributes computation across a type hierarchy. By the end of this session, you should be able to define what a recursive data type is and write a formal data type definition. You should be able to implement immutable lists using empty and cons, implement operations using the interpreter pattern, and explain structural sharing. You should also be able to distinguish static from dynamic types, explain why utesinits is dangerous, and apply recursive types to Boolean formulas and backtracking. A recursive function is defined in terms of itself. A recursive data type is defined in terms of itself in the same way. These types have two variants. The base case variant is the simplest, non-recursive form, for example, an empty list. The recursive case variant contains an instance of the same type, for example, a list head combined with a tail, which is itself a list. The code structure naturally mirrors the data shape. This correspondence is the source of elegance in recursive types. Let us review the recursion concepts that underpin recursive data types. The base case is the simplest, non-recursive scenario, an empty list or a leaf node in a tree. The recursive case reduces the problem to a smaller subproblem of the same type. Termination is guaranteed when recursive cases always reduce toward the base case. Recursive types are typically list-like, recursing on the tail, or tree-like, recursing on left and right subtrees. We will use imlist of element as our running example throughout this lecture. Why immutability? Immutability enables structural sharing. Two different list objects can safely share the same tail in memory. One list's operations cannot affect another that shares its suffix. This leads to reduced memory, no need to copy shared suffixes, and faster construction. Prepending an element is O of 1, not O of n. Immutable lists are not just simpler to reason about, they are often more efficient than their mutable counterparts. Imlist has four fundamental operations. Empty takes no arguments and returns the empty list. Cons takes an element and a list and returns a new list with the element prepended to the front. First takes a non-empty imlist and returns its first element. Rest takes a non-empty imlist and returns the list minus the first element. These four operations originate from Lisp in 1958. In functional programming, first and rest are often called head and tail. The operations cons first and rest are mathematically linked. First of cons of E and L equals E. Rest of cons of E and L equals L. What cons puts together first and rest peel apart? In TypeScript, calling empty.cons, 3.cons, 2.cons 1 creates the list 1, 2, 3. The first element is 1. The rest is 2, 3, and rest.rest.first is 3. This mathematical relationship is what makes the operations coherent as a system. Here is the imlist interface in TypeScript. Cons takes an element E and returns a new imlist with E prepended to the front. First is a readable property that returns the first element. It throws an error if the list is empty. Rest is a readable property that returns all elements except the first. It also throws if the list is empty. The element type parameter is filled in at usage. Imlist of number, imlist of string, and so on. To implement imlist, we need exactly two classes, one for each variant. Empty represents the empty list, the base case. Cons represents one element prepended to another list, the recursive case. Both classes implement the same imlist interface. The interface defines what every list can do. The variant classes define how, based on whether the list is empty or not. We provide a factory function empty rather than exposing the empty class directly to clients. If a client writes new empty directly, they depend on the concrete class name. If we ever rename or replace empty, that client breaks. The factory function returns imlist of E, hiding the concrete class name completely. The factory function is the only place in the codebase that mentions empty. Changing the representation requires updating exactly that one line. TypeScript's parameter properties provide a shortcut that combines field declaration and assignment in a single line. In the cons class, the constructor declares public readable first and public readable rest as parameter properties. TypeScript automatically creates the fields and assigns the constructor arguments to them. The cons method creates a new cons with the element at the front and this list as the tail. A note on public fields: they are safe here only because imlist is immutable. Reading a field cannot corrupt the rep. Because imlist is immutable, aliasing is completely safe. Start with x equal to the list 1, 2, 3. Create y by prepending 0. Y is 0, 1, 2, 3. In memory, y is simply cons of 0 and x. The tail of y is x, the same object, not a copy. Modifying y is impossible. The type is immutable, so x is never at risk. Insurmountable data structures enable safe sharing at zero copying cost. We write a formal data type definition to express the recursive structure precisely. Imlist of E equals empty plus cons of first colon E rest colon imlist of E. The left side is the abstract data type name. The right side is the variance, joined by a plus sign indicating union. Empty has no fields, it is the base case. Cons has two fields. The second field, rest, is recursively imlist of E. This is where the recursion lives. Always include this definition as a comment before the variant classes. The data type definition generates an infinite family of possible values. Starting from empty, the empty list, and applying cons repeatedly, we build every possible list. Cons of true and empty gives the list containing just true. Cons of true and cons of false and empty gives the list true, false. We can build lists of any length. The definition is finite. The family of values it describes is infinite. This is the power of a recursive definition. This style of type definition, a type is one of these variants, is called an algebraic data type in functional programming. You see this pattern in Haskell, ML, Rust, and Swift. In this course, we implement algebraic data types using an interface for the abstract type and classes for the variants. The data type definition as a comment before the variant classes is a documentation discipline we follow consistently. It makes the recursive structure immediately visible to any reader of the code. The same variant pattern applies to tree-like structures. Tree of E equals empty plus node of value colon E. Left colon tree of E, right colon tree of E. The tree diagram shows a binary search tree. The root is 5. 5's left subtree contains 3, and 3's subtrees contain 1 and 4. 5's right subtree is the leaf 8. Each node holds a value and 2 subtrees. Each subtree is itself a tree. Empty is the leaf, the base case where recursion stops. The variant structure provides a template for implementing operations. The pattern has 3 steps. First, declare the operation in the interface. Second, implement the base case in empty. Third, implement the recursive case in cons, usually by calling the same operation on rest. This is called the interpreter pattern, distributing the logic of an operation across the class hierarchy. The code structure mirrors the data structure. Here's the interpreter pattern applied to size and is empty. Both methods are declared in the imlist interface. In empty, size returns 0. The empty list has no elements. Is empty returns true. In cons, size returns 1 plus this dot rest dot size, the recursive case. Is empty returns false. Notice how natural this is. The recursion in the code mirrors the recursion in the data structure. Let us trace through size for the list A, B, C. Size of cons of A and cons of B and cons of C and empty. That is 1 plus size of cons of B and cons of C and empty, which is 1 plus 1 plus size of cons of C and empty, which is 1 plus 1 plus 1 plus size of empty, which is 1 plus 1 plus 1 plus 0, which is 3. The recursion unwinds 1 cons at a time, contributing 1 per element until empty contributes 0. Here is concat traced through the interpreter pattern. Concat of empty and list 2 is simply list 2, the base case. Concat of cons of first and rest and list 2 is cons of first and concat of rest and list 2, the recursive case. Trace for concat of the list A, B, and the list C, D. First, cons of A in front of concat of the list B and C, D. Then cons of A in front of cons of B in front of concat of empty and C, D. Then cons of A in front of cons of B in front of C, D. Result, the list A, B, C, D. The first list is peeled back one element at a time, rebuilding it in front of the second. The size operation as written traverses the entire list, O of n. We can make it O of 1 by caching the size in the cons class at construction time. The constructor computes cached size as 1 plus rest.size and stores it. The size method simply returns cached size. This is a benevolent side effect at construction time. The abstract value, the list contents, does not change. Only the performance does. After construction, every call to size is instant, regardless of list length. Clients know only the imlist interface. They must not know whether the implementation uses empty and cons or some other structure. Is it safe to return rest from the cons class? Yes, because imlist is immutable. Even if a client holds a reference to the internal rest list, they cannot mutate it. Rep exposure only threatens us when the returned object can be modified. Immutability and rep independence reinforce each other perfectly. When mutation is impossible, aliasing is harmless. A common mistake is using null or undefined for the base case of a recursive type. If you represent the empty list as null, every method call requires a null check before proceeding. If list is not null, then list.size. These guards clutter every piece of code that uses the type. The Sentinel object pattern uses empty instead. Empty is a real object that implements imlist. You can call size on it. You can call cons on it. It behaves correctly without any null check anywhere. Zero null checks required ever. Two important terms, static type and dynamic type. The static type is determined at compile time based on the variable declaration or type inference. The dynamic type is determined at runtime based on which constructor was actually called. In the example, X is declared as imlist of number, that is the static type. The object in memory was created by the empty constructor, that is the dynamic type empty of number. The compiler checks operations against the static type. The runtime dispatches method calls based on the dynamic type. This is dynamic dispatch, the mechanism that makes polymorphism work. Avoid inspecting runtime types with authentices for variant selection. Writing if list authentices cons, then use list.first is not recommended. Why? If a new variant is added, say a catching list, the compiler does not warn you that your authenticize checks are now incomplete. You get runtime errors instead of compile errors. Extending the type with new variants requires hunting down every authentices chain in the codebase. And it forces knowledge of concrete classes into code that should only use the interface. Instance of breaks all three of our core goals. The alternative, add observer operations to the interface. Declare is empty in the imlist interface. Every variant implements it correctly. Instead of checking if list auth is empty, check if list dot is empty. Logic stays above the abstraction barrier. Adding a new variant just requires implementing is empty correctly in that class. All existing code continues to work without changes. Observer methods extend cleanly. Osif is chains do not. Implementing equal value for a recursive type has two options. Option 1 is observer-based. Use size and positional access to compare the two lists element by element. This works even if there are multiple implementations of imlist and stays entirely at the interface level. Option 2 uses auth-sys. Check if both are empty or both are cons. Compare first, then recurse on rest. The ASPIR-based approach is generally avoided, but equality for recursive types is one of the few cases where it is considered the least bad option, because the recursive structure naturally drives the comparison. Recursive types excel at representing syntax trees, expressions that contain sub-expressions. The formula type has 4 variants. Variable holds a name, not wraps a formula, and holds 2 sub-formulas, or also holds 2 sub-formulas. The formula P or Q, all and ed with not P or R becomes and of, or of variable P and variable Q, and/or of not of variable p and variable r. This is the abstract syntax tree of the formula. Operations like evaluate, which assigns truth values to variables, and variables, which collects all variable names, are implemented recursively, one case per variant. Imbrimbled recursive types are ideal for backtracking search, exploring choices, and abandoning failed paths. With mutable data, you must manually undo every choice when backtracking. One forgotten undo permanently corrupts the state. With immutable data, there is nothing to undo. Just stop using the current branch and return to the previous shared state. Each step in the search shares a suffix with all previous steps at zero extra cost. Backtracking becomes as simple as returning from a function call. The previous state is always preserved. Immutability is not always slower. The comparison depends on the usage pattern. For structures with many in-place edits to the same location, mutable updates can be faster. For shared and read-heavy structures, immutable data requires zero defensive copies. Aliasing is safe. For concurrent access, immutable data needs no locks because mutation is impossible. For backtracking, immutable data makes undo trivial. Old state is always preserved. Structural sharing means immutable updates are often O of 1 or O of log n in well-designed implementations. Let us summarize the key ideas from this lecture. A recursive data type is defined in terms of itself with base and recursive variants. The data type definition uses the notation T equals variant 1 plus variant 2. The interpreter pattern places one method per variant, making code structure mirror data structure. Structural sharing makes aliasing safe with no copying required. Sentinel objects like empty eliminate null checks everywhere. Dynamic dispatch selects the method based on the object's dynamic type. And instead of interfaces, add observer operations to the interface. These ideas together form a powerful foundation for building complex, correct data structures.